Here we go. Welcome back, ladies and gentlemen. We're looking at efficiency today, the efficiency of a simple machine. Now, we learned yesterday about the mechanical advantage and what that number means to us. And today we're going to be looking at the efficiency. And really what it's telling us is how efficient is the machine at transferring input energy or stuff that you're doing into the machine to creating it to be output energy or the work to be done. And it's a percent measure of how much of the work put into a simple machine is transformed into useful output work by the machine. Let's give you an example then. So let's say you are trying to pry up a rock in your yard and you've got this lever set up and you push down on the lever. If the lever is 100% efficient, that means it's going to lift the rock up for you when you push down on the lever. If it's 0% efficient, that means the rock doesn't even move at all when you use the simple machine. So it's one of those things, as we talked about the mechanical advantage, meaning that it's multiplying your input force, is what the mechanical advantage does. Then the efficiency shows you how efficient the machine is at doing its job. Again, transferring your input energy, which is really what it is, it's an energy, into then usable output, and then subsequently doing the job of what the machine is trying to do then. So let's kind of take a look at that. Maybe let's look at the equation. Maybe that'll kind of help us out here with that. So if we take a look at the equation then, we've kind of got efficiency. Here we go. The efficiency is the work output divided by the work input. So WO divided by WI. So remember, work is again a force times a distance. So you now have an output force and an output distance divided by the input force and input distance. That then number, you take those two numbers, divide them out, times 100, then gives you the percent efficiency of the simple machine. You can also then solve for the work output by taking the efficiency times the work input. Now, when you take the efficiency, remember we got to change the percentage back into a decimal point. So that's always one of the things we need to be mindful of. And we can also then solve for the work input by taking the work output divided by the efficiency. Again, both of those works, the work output and the work input, are measured with joules, which again is a measure of energy for us, and it's also how we measure our work. So the key to it being is the fact that, yeah, you got a lot of numbers here. You're going to have kind of a fairly complicated problem, but for the most part, you should hopefully find this to be fairly simple, as I was kind of try to outline here when we look down below at these other equations now. So what I've tried to do now is to single out then the different parts to this overall equation. So again, the work output force. So as we kind of go through these here, the work output force will be the object's weight. It's the thing that you're trying to do work upon, whether it be the rock, the window, a box, a cow, whatever it is. It's the thing that you're doing the work to. It's the object's weight. And we can find the work output force by taking the efficiency times the quantity of the work input force times the work input distance divided by the work output distance. So what you're going to want to do is you're going to want to make sure that you multiply the input force and the input distance together first. Take that answer times the efficiency, divide that by the work output distance, will give you the work output force. So as you can kind of see in the problem down below, or in the diagram down below, that would be the object of the weight of the object. Also over here too in our lever, it's the weight of the object. Now the work output distance then will be how far the object moves, whether you're going to the height of the inclined plane or whether you're looking at then how high the object then moves using the lever. So the work output distance is how far the object moves. It's basically what's being done to the object. You can find the work output distance by taking the efficiency then times the work input force times the work input distance, that quantity, divided by the work output force. So again, do the same thing. Work input force times work input distance equals then times your efficiency equals divided by the work output force will give you then the distance the object moves. Now the next one, the work input force. And so again, it's very similar to the mechanical advantages, the fact that it's a push or pull, a lift, it's the exertion, it's what you are doing to the object then. If we think about our lever, here it's what you're pushing down on the lever. We think our inclined plane, it's you pushing on the object to push it up the inclined plane. That would be our work input force. We can find the work input force then by taking the work output distance times the work output force divided by the efficiency times the work input distance. So solve for both top and bottom and then divide, and you'll find the work input force. And the last one would be then the work input distance. And what this is saying is then the distance you are exerting. So when we think about then our lever here, here's our work input distance. It's how far the lever is actually going down. When we think about our inclined plane, right, you follow the arrow going across, and it's how far then you actually push up on you're going up the inclined plane would be your work input distance. And you can solve for that equation by taking the work output force times the work output distance divided by the efficiency times the work input force. Now, the key to solving all of these efficiency problems, which we're going to see here on the next page when we look at our practice problems, the key to solving these things is drawing a picture. If you can draw the picture and then get the numbers in the right spot, it makes it so much easier then. And that's kind of going to be the big key with this one here. So let's just take a look at number one here. A lever requires 600 newtons of force moving 2 meters downward to raise a 700 Newton rock 1.5 meters off the ground. What's the efficiency of the lever? So again, we're looking for the efficiency. Efficiency is going to be the work output divided by the work input. So now remember, what we're going to need then is the work output force times the work output distance divided by the work input force times the work input distance. I know you might be thinking to yourself, this is going to get really confusing. But if we draw the picture, you're going to find that it's really not that bad. So what we've got here, here's our lever, here's our object. So a lever requires 600 newtons of force moving 2 meters downward. So here's our 600 newtons of force. The lever has to go then 2 meters downward. To raise a 750 Newton rock, 750 Newton rock, 1.5 meters off the ground. There we go. So again, if you can draw the picture, now we can label the parts to these then. So again, because we're pushing down on the lever, this would be our work input force. And because we're inputting for this measure downward, we're now going to say here's our work input distance. Now again, the output force will always be the weight of the object. So here's our work output force. And here's now our work output distance and how far the rock actually moved then. So now all we kind of have to do is hopefully make this as simple as we can, find the problem, or put our numbers and kind of plug and chug as we go into. The work output force, 750, times the work output distance of 1.5, divided by the input force, which is 600, times the input distance, which is 2. So now we're going to need your calculator out, so we're going to have 750, hold on here, 750, there we go, times 1.5. And that equals 1125 joules, because again, it still is work. And we're going to take 600 times 2, which is 1200. So now 1125 divided by 1200, and that's going to equal then 0.9375. But remember, we want to find the efficiency. We're going to multiply that by 100, and we end up with 93.75%. And there's our final answer to that. So while I know the equation looks big, and I get that, and I also think that when hopefully you see then the diagram or the picture of it, you can kind of go, okay, now I see how these kind of pieces all get put together. And so really what it says is your efficiency with a 93.75% efficiency should what it's telling you is that if you use 600 newtons of force moving 2 meters downward and you're trying to raise a rock that's 750 newtons of force 1.5 meters off the ground, with a 93.75% efficiency, it should be really easy. You shouldn't have to be pushing down on the lever very hard because your lever itself, the simple machine, is extremely efficient at what it's doing. So it should be really easy for you to do. So again, with all these problems, draw pictures with them. It really will help you to do any of the things that as much as you can. So a simple machine here, number 3, has an efficiency of 65%. And the question is, what will be the machine's work output if the work input is 5,000 joules? So again, we're going to go back to our equation here. What will be the machine's work output? The work output would be equal to the efficiency times the work input. So with our efficiency of 65%, we're going to change that to a decimal of 0.65 times the work output, which is then 5,000. And what you're going to find then is 0.65 times 5,000 is 3,250 joules. And there's your answer for that one. So again, always kind of keep looking at what the equation is giving you, draw your picture, find the places that you can substitute the numbers in for your labels, and then you can plug and chug in your calculator. Hopefully that makes things a little bit easier for you to find the efficiency then of simple machines. If you have any questions or problems, please feel free to call or email me again, and have a great day.